Imagine taking a tiny, lightweight, totally unassuming hatchback, popping the hood, and deciding to cram not one, but two completely different, highly complex forced induction systems in there. I mean, it's a level of engineering audacity you just rarely see, and it absolutely redefined what a small displacement engine could do. Welcome to this explainer. Today we are dissecting a true mechanical marvel, the legendary Nissan March Super Turbo. The magic number for us today is 2. In the automotive world, you generally just pick one path for forcing extra air into an engine. You either go with a supercharger or a turbocharger. But Nissan, they decided to engineer a single vehicle with 2 distinct forced induction systems working together in tandem. It's an absolute anomaly that requires a mesmerizing level of mechanical orchestration. Here's the roadmap for our mechanical dissection today. First, we'll meet the Super Turbo, then dive into the twin-charged solution, trace the exact path of power, see how the ECU controls the chaos, and finally wrap up with its real-world legacy. Let's get right into it. Section 1. Meet the Super Turbo, mechanical foundation. Okay, let's establish our baseline. We're starting with a super robust inline 4-cylinder engine utilizing a single overhead cam, or SOHC valve train. Now, on the surface, the fuel injection, cooling, and lubrication systems look pretty standard for a combustion engine of its era. But you have to look at that bottom row, twin-charged forced induction. This entire block, the cylinders and the cooling system, all had to be heavily engineered to withstand massive amounts of internal pressure and heat that a normal engine would literally never experience. Section 2, the twin-charged solution, eliminating lag. So, what was the big engineering problem Nissan was desperately trying to solve here? Well, it all comes down to the inherent trade-offs of traditional forced induction. See, a turbocharger relies on exhaust gases to spin up. This makes it incredibly efficient at high RPMs, but it suffers from low-end lag when you first step on the gas pedal. On the flip side, a supercharger is driven directly by the engine's belt. This gives you instant, explosive low-end power, but as engine speeds climb, it creates a parasitic loss. It literally robs engine power just to keep its own rotors spinning. For decades, engineers just had to accept this compromise. That is, until Nissan looked at the problem and thought, hey, why not just combine them? The ultimate solution? Twin charging. By physically pairing both systems, the goal was to completely wipe out that annoying turbo lag at the bottom end, while simultaneously maximizing high-end boost at the top end. If orchestrated perfectly, it acts as the absolute engineering sweet spot. Section 3. The path of power, a chronological journey. Let's literally follow an air molecule from the outside world straight into the combustion chamber to see how this builds forward momentum. It's kind of like a high-speed relay race. First, outside air gets sucked through the air filter and intake duct. From there, it is drawn directly into the supercharger for its first round of compression. Then, it's pushed through the intercooler to drop the temperature. Next, it routes right into the turbocharger for a second, massive round of compression, before finally being forced into the intake manifold and down into the cylinder head. It is a highly complex, high-velocity relay race. Let's zoom in on the first runner in this relay, the supercharger. Think of this as a mechanically driven air compressor packed with interlocking rotors. Because it's connected directly to the engine's accessory drive belt, its RPMs rise the exact millisecond the engine RPMs rise. This forces extra, densely packed air into the engine immediately. It's exactly what gives this car its famously violent, zero-lag launch from a standstill. Now, you might remember that high RPM parasitic loss we talked about earlier, right? Well, Nissan solved that brilliantly. They slapped an electromagnetic clutch right onto the supercharger pulley. Using an electrical coil and a magnetic field, this clutch can physically engage or completely disengage the supercharger from the engine belt based purely on RPM. When it disengages, boom, it completely eliminates that parasitic drag. But wait, why is it safe to just turn the supercharger off? Well, that's where the turbocharger comes in. Unlike the belt-driven supercharger, the turbo utilizes waste exhaust gas escaping the engine to spin a turbine, which in turn spins a compressor wheel. Once the engine hits mid to high RPMs, there is more than enough exhaust gas flowing to make the turbocharger highly efficient, allowing it to easily take over the heavy lifting of power production. And this brings us to the absolute climax of this engine's operation, the handoff. This is that incredibly precise, calculated window where the electromagnetic clutch disengages the supercharger and the fully spooled turbocharger takes over the entire forced induction workload. It requires absolute mechanical perfection to keep you, the driver, from feeling a sudden, jarring drop in power. This torque generation across the RPM band really illustrates why that handoff is just so vital. At low RPMs, the supercharger is doing the work, giving you this massive instant spike in torque. In the mid RPMs, you have this transition period where both systems are technically overlapping to maintain the pressure. And then at high RPMs, the supercharger completely cuts out and the turbocharger takes that massive wave of power all the way to redline. The resulting acceleration curve feels incredibly unique behind the wheel. Now there's a catch. Compressing air through both a supercharger and a turbocharger creates a massive amount of extreme heat. That's exactly why the intercooler is strategically planted right in the airflow path. It's a heat exchanger made up of a specialized core and fins. As the scorching hot compressed air passes through, heat is transferred out. Why does this matter to us? Because cooler air has higher density. Higher air density means you are packing way more oxygen molecules into the combustion chamber, giving you a significantly more powerful and, crucially, a safer combustion stroke. Section 4. Controlling the chaos. Synchronization. So, with all these belts spinning, clutches grabbing, and turbines spooling at tens of thousands of RPMs, how does it all stay in perfect sync? The answer is the engine control unit, or the ECU. I want you to think of the ECU as the orchestra conductor. It is the electronic brain of the whole operation. By constantly monitoring a vast network of sensors, it manages the fuel injectors, the ignition timing, and most crucially, the delicate balancing act of boost pressure between the supercharger and the turbocharger. Let's see exactly what this conductor is actually managing behind the scenes. The ECU uses sensors to constantly monitor how far you've pressed the throttle and the exact massive airflow entering the engine. Based on those triggers, it sends the electrical current to engage or disengage the supercharger's clutch at the exact right millisecond. Simultaneously, it manages the turbo's wastegate to prevent dangerous pressure spikes, it balances the air-fuel ratio so the engine doesn't run too lean or too rich, and it dictates the spark plug ignition timing to prevent engine knock. It is busy. But physically managing that intense airflow during the transition requires one more absolutely critical piece of hardware: the bypass valve. This is basically a pressure balancing vacuum valve. Think about it, when the supercharger clutch disengages and the rotors stop spinning, they essentially become a giant physical roadblock for the incoming air. So the bypass valve instantly opens, redirecting the high-velocity airflow completely around the dormant supercharger so it can flow straight into the turbocharger without losing any pressure or causing compressor surge. Section 5. The real-world legacy, driving and maintenance. All right, let's step out of the engine bay for a second and look at the real world. What is this actually like to drive? Well, this complex engineering translates into something truly magical behind the wheel. You get a perfectly smooth, instant cold start idle. In stop-and-go city driving, the supercharger provides literal zero-lag acceleration, darting you through traffic. Then when you get on the highway and drop a gear to pass someone, the turbocharger delivers this seamless, rushing top-end power. It takes a tiny economy car and gives it the dynamic, aggressive driving characteristics of a much larger sports car. Of course, we have to look at the trade-offs fairly. Jamming all this hardware into a tiny engine bay results in extreme packaging complexity and incredibly high heat generation, which naturally degrades components faster. You have totally unique failure points, like the supercharger clutch wearing out. Plus, because of the absolute labyrinth of piping, valves, and intercoolers, you run a very high risk of vacuum and boost leaks. A single cracked hose ruins the entire symphony. Because of this, it demands incredibly strict, relentless maintenance intervals for oil, belts, and spark plugs. Ultimately, the Nissan March Super Turbo remains a true masterclass in automotive innovation. Sure, modern turbocharging tech and computerized twin turbo setups have largely made twin charging a thing of the past for mass production, but this specific engine stands out as a legendary, innovative anomaly. It represents an era where engineers solved complex drivability issues with sheer mechanical brilliance rather than just writing a line of code. Which brings me to a final thought for us to chew on. As modern automotive engineering shifts heavily toward electric motors, which, naturally provide 100% instant low-end torque without a single drop of lag, was the twin-charged engine the ultimate mechanical solution to a problem we simply no longer have? Thank you so much for joining me on this explainer. Keep learning and keep questioning how things work.